All right, everybody. Hey, welcome. And this is, I guess, my fourth video solution. And I'll go ahead and get started here. I better stop counting them because I know I'm going to start messing up here now. And there's a really good question that's been asked by a lot. In fact, in today's Zoom sessions, it was asked even a couple of times, I think in the first session, and then I did it again in the third one. And it is number 60. And so chapter 23, number 60. And I don't know, maybe everybody who had this question it already got answered in the Zoom session, but I was thinking maybe not. But more than that, I was thinking that there's some neat little piece of advice that I want to give here. And so I thought it would be worth running through. So let me read it here. The problem says this. It says, consider the charge distribution as shown in the figure. So I printed up the figure here so you guys could see it. Or at least that's half the reason. The other half is really what I want to talk about here. And so it says, A, show that the magnitude of the electric field at the center of the face of a cube has the following value, 2.18 coulombs constant times the charge divided by the side squared. And then it goes on to B, what direction is the electric field at the center of the top? But here's the part I really wanted to emphasize here, is that these problems, probably more than any other physics problem you've ever seen, really need to be done half of with the physics and the other half with the math. And so having a good conceptual understanding and a good physical and visual picture of what's going on is crucial. And this one illustrates it really, really well, because it sounds like it's going to be a pretty hard problem at first. In fact, the author even labels it as a hard one, and he labels his problems as easy, medium, and hard. And this one is listed as hard. And it's not hard really once you see what I want you to see or what I'm about to say. So in part A, and if you can kind of see this three-dimensional cube, and that's why I printed it, because it was better than I could draw. And I go to the top right here, right at the center of this top face, okay? So I'll make kind of a point right there. So I'm at the center of this top face. And your author says, okay, go ahead then and figure out what the electric field here is at the top. And here's where a lot of good physics can save you a lot of work and a lot of thinking. Look at this charge right here. Now, they don't really say whether it's positive or negative, but let's just assume for the sake of argument that it's positive. This charge would make an electric field pointing over towards this charge. Maybe I drew the arrowhead too big. I kind of covered that one. But what I want you to also see then is this charge that I've now covered would make an electric field pointing that way. And since we know the equation for the point charge is this, these two have the same charge, Q. They're also the same distance away from that point. So they would make an electric field, excuse me, that is equal in magnitude, but opposite in direction. And so those come out to be 0. So even though the electric field is made up of all 8 charges that are on the corners of this cube, these two cancel off. And then of course, watch the left and right. And so this one here makes an electric field that way. And this one here makes an electric field that way. And so it too would cancel out. So what started off looking like a pretty challenging problem, it's first of all, it's three-dimensional. Those are always harder. And second of all, it's got 8 charges, so I got to add up all these points and some crazy angle between them. I've now cut that work in half. I now have realized that I don't really need to do any calculations based on just the physical picture to figure out what the electric field is there. I couldn't get the electric field then, the total electric field, although I'm technically adding up all 8. I only have to add up the bottom 4 because the top 4 came out to be 0. And it even gets better. Watch this. Let's look at the electric field from this bottom left corner here along the x-axis. And so at this point here, it might be kind of hard to visualize in this flat surface that I'm trying to draw in 3 dimensions, but it would kind of be angled out and, some angle directly, along that line. In fact, maybe it would help if I kind of drew a line from this charge to it. And so maybe you could see it better if I drop straight down. It would go right in the center of the bottom square and then across. And so I would have a triangle here. And so that would be the electric field from this one. But watch this. And I hope my picture's not getting too cluttered. Look at the one across here. The one across here would be something like this. And I claim that this electric field created from this charge, and this electric field created from that charge, these two would be the same magnitude and the same angle, if you will, above this top face of the cube. And why that's important, and maybe a different color will make it stand out, is if you look at this first electric field, it would have a vertical component and a horizontal component. So it would go up and to the right. This one here would go up the same amount and to the left the same amount. And that's an important key there, that these left and right components, they're really kind of at an angle, so it's kind of right and back, and this is kind of left and forward. But those two are going to cancel each other. And so I can make this a little bit easier on myself by saying, let's not worry about both of these, because when we consider both of these, the x component or the left and right go away. And look at this. The same can be said with those two. Maybe I better not try to draw it in there, but they would, this one would come back at an angle that way, and this one would come forward at an angle that way. And they would look just like these. And so the horizontal components of these two would cancel off. And so here's the neat thing about it. Even though I'm adding up all 8 charges, I'll say it again, the first 4 I don't even need to worry about. And as far as the bottom 4 go, thinking of them in pairs, these pairs and then these pairs, the horizontal stuff cancels off. So I don't even have to do horizontal. So the end of this is only in the z direction. That's all physics so far. I've just been looking at the angles of the electric field and the geometry. I mean, I guess I've done a little bit of math there, realizing that the angles and the magnitudes have to match up just right. But with giving this some thought, I have turned what looked like was going to be in a hard problem to a lot easier problem. In fact, here's the final step, because not only do these bottom 4 cancel in terms of horizontal, in terms of the vertical, then all 4 of these have the same vertical component. And so I would say the best way to do this problem is to first calculate the vertical component of one, and I'll just say one of the charges, and I better say on the bottom, and then figure what that is and multiply by 4, because all 4 of these add together. Ta-da! And so that's now going to make this problem easy. So I'm pretty sure that's why your author put this as a magenta one, because students would be tempted to figure out the field from all 8 of them and start adding them together. And of course, if they did all that right, they would certainly get it right. But if they would have noticed that these 4, by the time you add up those 4, you come up with 0, and that was just unnecessary work. And then the plane, the x components of these and the y components of these, those would cancel off. And then you're only left with the I'm sorry, these are z components, a vertical component on this grid. I put a y, but I want to match your author's grid system. He's calling up a z. Okay, so that would be z. So with that in mind here, actually maybe I'll just keep working on this page now that I've drawn on it. But I can't emphasize enough that I've made what looked like was going to be a hard one and an easy one. Although there's still something hard about it. So let's do this. Let's see if we can find then the z component. Now, the z component would be the magnitude of it. So coming back to the picture here, I'd be looking, okay, that magnitude. And then if we called this angle right in here theta, then it would be adjacent to it, so it would be cosine of theta. So electric field from that one only multiplied by cosine of that angle theta would give me the z component of it, and then of course multiplied by 4, we're done with the problem. All right, so let's go to the equation for a single point. That is Coulomb's constant times charge q, so that's charge q and Coulomb's constant, divided by, the distance away. Now, here's going to take some thought. Let me highlight this triangle that we have done earlier. That is a drop down here and kind of along the diagonal of the base and then here. So that does make a right angle triangle. There's the right angle. So if I could figure out how far down it is, so how far down, and if you look here, that's just the drop of the cube, so I'll call that S. And then how far over, then I could use Pythagorean's theorem to find that distance. So that's what I'll do. Now, to get how far over this is, maybe I will just draw right here, so it's more of in a flat plane, this bottom square. So we're looking at from this point here out to the center as being this line there. And I would say that is half the whole diagonal of it. And if this is S and this is S, then we've got Pythagorean's theorem here also. So we've got S squared plus S squared equals, and for lack of better symbol, I'll just call it C squared. And so this is 2S squared is equal to C squared, or C is square root of 2S. Now, of course, I want half of that. So this right here, that is that distance right there, would be that cut in half. So this would be the square root of 2 over 2 times S. So there is that distance. So now I can get this distance squared. This would be square root of 2 over 2S squared. And then this would be S squared. And so that is the square of the distance. And remember, the equation back up here is distance squared. So I'm not going to bother to take the square root of that and just square it again. That is the distance squared. Now, another fun piece of this right here is the angle theta. It's actually cosine of theta. So remember, I've labeled theta up here, but that translates down to this angle, which in this picture would be right there. So this is theta. So cosine of theta would be the adjacent, so that's S, over the hypotenuse. And maybe I'll just put a square bracket around this. We said this was the distance squared, so it would be the square root of that. So it would be another square root of 2 over 2S squared plus S squared to the 1/2 power. So that's the r. Remember, this one is r squared. And so we could even put those together. So this would be square root of 2 over 2s squared plus s squared to the 3/2 power. And then in the numerator, we would have Coulomb's constant, Q, and S. And we can simplify the bottom here a little bit. I'll start with the s's. This has an s squared and this has an s squared, so I'll bring it out to here, s squared. But if I also then say that the s squared factors out of these two terms, so I'll factor out of those two terms, and so I'll put it here as an s squared, but it's s squared raised to the 3/2 power. So both of these factors would be to the 3/2 power, remembering that, you know, xy to the mth power is x to the mth and y to the mth. All right. And of course, this one is nice because a square and a square root cancel, and that's just s cubed. And then there's an s there. So that would become Coulomb's constant Q, and that s with an s cubed makes an s squared. And then, of course, back to this one right here. This one, since we factored out the s, that's not there anymore, the s squared, that whole discussion. We would have this squared, and so you square that, that's a 2, you square that to 4, so that's a 2 over 4. And 2 over 4 is 1/2. And then that was just left with a 1. So that becomes 1.5, which I'll write as 3 over 2 to the 3/2 power. And then maybe two more steps here is to say, now to get the total electric field, we need to multiply by 4. That was that discussion earlier about right there. And hopefully we have the correct number, because let's see what we get when we put the calculator here. There's the 4. Actually, let me do this harder one first. Well, now I'll just do it all in one shot. So there is 4 divided by, and I'll just write this as a decimal, 1.5 raised to a power of 1.5. And there it is, 218. So 2.18 are our numbers. Coulomb's constant times Q over S squared is what they say, show that that's what it should come out to be. So sure enough. And essentially, we've also answered B, because B says which direction. And so we're saying this is, you know, the up. Maybe to write it as a vector, we should say equals, and we can write it as a vector with a k hat. And so on this one, it's pointing up, the top face up. And then, of course, all of these other faces would be outward, away from the cube. So here would be along the y-axis, and here would be along the x-axis, and well, here we just did along the z-axis, and on this back face over here would be the negative y-axis, and this back face over here, the negative x-axis, and this bottom face right here would be going down in the negative z direction. All right, hopefully that was helpful.